Okay, thank you. Thank you for the introduction and for having me. It's a great pleasure to be here discussing about the way people with autism perceive themselves in space and in different environments. I'm a second-year PhD student at the University of Padua in Italy, and I'm working on multisensory development. So I would love to start with saying that our reliance on different sensory cues depends on the variability of that information and that sensory modality, which is not stable, but rather varies in different tasks, environments, and most importantly, across ages and developmental trajectories. So I'm going to focus on the integration between vision and proprioception, which is fundamental for moving in a real world and also in the virtual one. And when defining proprioception, we know that we refer to the sense of where our body is in space. And of course, it comes from somatosensory and neuromuscular information, but it is also important to remark that vision has an important role in calibrating proprioception coming from the bodily cues, let's say. So, for example, let's think about the rubber hand illusion, where we can create proprioceptive sensation towards a rubber hand just by providing the subject, the participant, with the synchronous visuotactile stimulation to a fake hand, basically, with a hidden real hand. So we are interested in the way children develop this ability to integrate vision and proprioception and then motor skills, because this is the basis for exploratory activities and learning in a broader sense. And when we look at the development, the typical development of visuoproprioceptive integration, we see that the visual contribution to body concept, body space, and awareness is not linearly developing, but rather changes at different ages. So we can see that at different ages, the relative contribution of vision to proprioception can be different, and this should be taken into account when studying development. And but overall, we know that vision is quite dominant in the first years of life. So children basically trust what they can see rather than what they can feel from other senses. And it's interesting to notice that proprioception is quite less reliable. For example, we can think about the huge amount of changes that the human body faces during the first years of life. And when looking at the research about autism, we know that in these conditions, people have an extended multisensory temporal binding window, which means that multisensory information are bounded together to a broader extent, to a greater extent. This is probably associated with a sort of sensory overload and a sort of unisensory facilitation, whereby children and also adults with autism are facilitated by poor, let's say, sensory environments without a number of sensory information coming from different sensory channels. And it's interesting to see that although we also have contradictory findings, but mainly research pointed that there seems to be a sort of hyper-reliance on proprioception. So these people probably is relying more on what happens inside the body rather than being hyper-relying on vision. So in a sort of neurocognitive isolation that sometimes prevent them to learn from the environment, the external world. And as this is associated to motor and social impairments, it's maybe interesting to investigate the potential of sensory interventions. And this is why I'm interested in virtual reality, basically, because this technology has the potential of excluding the real world and immersing the user and the individual in a new and maybe confounded perceptual experiences, thus manipulating and disentangling those multisensory cues that in real worlds are bounded together. And we can study the relative contribution, for example, of different sensory modalities. It is interesting to see that it has been suggested that sensory conflict between vision and proprioception may arise from virtual environments. We can, for example, think that we can see ourselves walking on the void while still perceiving the floor under our feet. And it seems that this is associated to the motion sickness we were talking about also with the other talks. And we can speculate and we can wonder whether these might differently affect users depending on their dominant reliance on both vision or proprioception, which are two different reference frames when navigating, moving, or orienting ourselves in space. And this is why I started wondering whether I could test the reliability of visual information and the extent to which particular kind of visual information can differently hide the proprioceptive-based self-motion. And I also wondered whether head-mounted displays and virtual realities compared to equivalent real environments would differently affect self-motion. I was particularly interested in studying these aspects across the lifespan and in particular in autism spectrum disorders. And this is why my colleagues and I designed and built this child-friendly, I hope, experimental room, where we can manipulate vision and perception in the same way we can easily do with virtual reality, so that we can compare virtual and real environments, being them equal from the perceptual point of view. And we choose a self-motion paradigm in which the experimenter rotates the participant to a certain degree, so from starting position to an end position, in a sort of passive rotation, let's say. And then the participant is asked to rotate back to the starting position, performing active rotation, so that we can measure their accuracy in perceiving and reproducing that body movement. And we prepared the room so that we could videotape the experiment, and we also videotaped the protractor under the swivel chair so that we can code the participant's performance offline. We have the within subjects design with the two main factors. We manipulated the sensory information available, thus creating 3 sensory conditions, and we also have the 2 environments, so reality and virtual reality. And we have 6 conditions resulting from the combination of these 2 factors. And I would just like to describe more in details the 3 sensory conditions. So we have the visual proprioceptive condition, let's say, where the participant could access either proprioceptive information and normal, let's say, visual information. So it is the visual information that allows the participants to see his or her own body, as well as the room corners. So in literature, these are the visual cues that are thought to be more informative from a proprioceptive point of view. So they really help people locate themselves in space. On the other hand, we have a sort of visual pattern made of clouds randomly fixed on the walls, and this creates a sort of visual flow that is the only visual information available in the only visual condition. So here we try to disrupt proprioception, but without directly removing the bodily signals, which is not really possible to do, I guess. But we try to do so by removing those visual information that are thought to be more informative from a proprioceptive point of view. So the participant in this case, thanks to the light system, could not see his or her body anymore, nor the room corners. And then we have the only proprioceptive condition. The dark was in complete darkness and no visual information were available. Our dependent variable, as I said before, were the errors in terms of degrees made by participants when coming back to the starting position. In the first study, we investigated these aspects in neurotypical children and adults with younger children aged from 4 to 8 years old and older children aged from 9 to 15 years old. And then we have the adults group. We embraced an exploratory an exploratory perspective, given that there is no much in literature to base on and clearly establish a priori hypothesis. But rather, we employ the Bayesian model comparison analysis to find the best model predicted by our data. And the best model predicted the main effect of age, so that younger children are expected to make greater errors, so self-motor errors, across conditions and compared to the older children and the adult groups. But we also find a main effect, a main interaction effect between environment and perception. So basically, we can expect participants to be less accurate in the only proprioceptive condition, so with no vision available. And we can also expect immersive virtual realities to disrupt this self-motion accuracy in those conditions that provide visual information, regardless of whether they were more or less informative from a proprioceptive point of view. And we also piloted this experiment with a small group of children and adults with autism. We recruited 4 children and 5 adults. They were all male. And still with an exploratory perspective, we can see some descriptive statistics and graphical visualization of this data. And it is worth mentioning that the sample was quite heterogeneous with comorbidities such as ADHD and moderate to mild and severe intellectual disability. And 2 out of the 4 children refused to take part into the experiment. So at the moment we have 2 participants. And 1 out of the 5 adults stopped the experiment at the very beginning. So we have 4 adults, let's say. At the group level, when we look at the participants' performance, we can see that they made smaller errors in reality in the only proprioceptive condition, so in darkness basically, which is different from what we have seen for typically developing people. And also it's in line with the hypothesis of an hyper-reliance on proprioception and hyper-reliance on vision for autism. And on the other hand, with in immersive virtual environments, they were overall more accurate with the only visual condition. This makes us speculate that maybe this technology can somehow increase the reliance on vision for people with autism. But of course, we had great inter-individual variability, so it is more informative to look at individual performance. We can see that in our sample, those participants who were generally more accurate in only proprioceptive condition across both the environments, they were also more accurate in immersive virtual reality compared to reality. So again, this makes us wonder whether there are 2 potential subgroups in our sample and whether virtual reality can better suit one of the 2 groups' needs, basically. So I would like to conclude with some open considerations rather than real conclusions. So in our 2 experiments, we mainly found a developmental trend in the improvement of self-motion accuracy across conditions, with 4 to 8 years old children showing reduced accuracy compared to older children and adults. So we are talking about something that has a long-lasting development. And we also found that virtual reality and headset seem to disrupt self-motion across the lifespans, and this might possibly be due to the way visual information are delivered with this technology. It was not related to the content of our visual manipulation in our sample, of course. And moreover, although we cannot generalize the results from our small sample of people with autism, we've seen that those who were facilitated by moving when only proprioception was available, they also benefited from IVR. So I think the most interesting speculation we can draw is that maybe virtual reality can either improve or worsen sensory motor performance of individuals, depending on the way they utilize vision and proprioception, for example. And as this multisensory functioning differs across individuals, maybe this should be carefully taken into consideration when designing interventions and maybe research. So I would like to thank my research group from the IEDE lab. We work with children with autism, but also my colleagues from the Psychostat group for bringing together psychology and statistics. And thank you all for your attention. Do not hesitate to ask any questions or get in contact if you have some later on.
Thank you very much. That was really interesting. I know I have a question straight away, but does anyone else have a question? I can see Tammy's got a question. Fire away, Tammy.
I just wondered what your study found with the sensory sensitivity that you mentioned to do with vision. You were saying that it's increased in your findings. Is that correct? Or
yeah, this is an interesting point. Maybe I was not particularly clear because unfortunately we didn't assess our participants' sensitivity to different stimulation. We just measured their motor accuracy when different information was available, basically. And what we found is that some of them, if we think about the autistic group, let's say, some of them were more accurate overall when no vision was available. And this is kind of different from what we can see from the neurotypical group, because of course we are more accurate when we can see while moving. And this might not be the case for them in this particular task, of course. And it was also interesting that those with this particular atypical use of proprioception, maybe, were also more accurate in virtual reality, let's say overall again. So without taking into account the interaction between the environment and the sensory information, because we didn't have so many participants, we didn't really look into that interaction. And that was investigated with the neurotypical children and adults. I'm not sure whether I responded.
That was interesting. Thank you for that. Yes, you answered my question. Thank you.
Thanks.
I think that would probably lead into maybe a question from David. I don't know if I'm reading your mind, but I feel like you're going to mention GSQ maybe.
No, I wasn't going to ask that, and excuse the cat that's going to come into my screen any minute now. But no, Irene, that was very interesting. But I just wondered, because you talk about proprioception and you talk about vision, and I just wondered, surely the vestibular system is involved in your experiment as well, if you're moving people, if they're rotating around actively. Or did I misunderstand something about your experiment?
No, I agree with you definitely. This is maybe related to the way we conceive proprioception. We think that proprioception is not a sense per se, but maybe something arising from different sensory information. So we are interested in the way we perceive our body in space. Let's call it, I don't know, self-motion accuracy or radar proprioceptive accuracy. But still, yeah, that's what we measured basically. And I agree that during the passive rotation, it was mainly the vestibular information, like contributing to this mechanism, but we didn't manipulate that particular sensory information that was always there and always kept constant. But while rotating back to the starting position, participants could maybe rely more on what we define proprioception in a sense, because they could like move their feet to come back to the starting position. So in that phase, proprioception were also involved.
Yes, of course, yeah.
But yeah, thank you for your question, because all reviewers pointed that out. So they made us think more about that.
Yeah. Okay.
Any other questions from anyone? I had just a bit of a random question. It's just because it occurred to me. So I thought it's a little bit more on the vision side. So maybe David might have more ideas on this. But just because it was children you've tested, and I know you kind of used the cave VR and then the sort of more immersive. So I think my questions kind of relates more to the immersive side, particularly because more the question around the stereo vision, and because it's developing quite late, like for a long time throughout the lifespan, and because it is such a wishy-washy topic, and autism in particular, and it is sort of a little bit confusing, I think, for just general neurotypical population. So I thought maybe, is it something that you particularly thought that was different from a vision perspective in the immersive VR in comparison to the cave? So it was a bit of a off-topic perhaps question, but I thought maybe
no, it's not. It's not. But I think maybe David Harris at the end of the conference will maybe expand on this. I hope so, because I've read his paper about the way the ventral and dorsal visual path is involved while interacting with immersive virtual reality due to the lack of depth cues and stuff like that. So yeah, it's interesting also because he suggested, and his colleagues suggested, that this is sort of part of the explanations to understand why vision is different in virtual reality. So they basically say that the action visual path is impaired, while the visual path that mainly involved the processing of object sizes and features and stuff like that is more involved. And there are also evidences about a sort of impairment in these two visual paths in autism. So it would be interesting to look more into that, but we are just at the speculation phase,
yeah.
I guess, to my knowledge.
Yeah, that we could go down the rabbit hole, because the vision is my pet peeve, so we could talk about this forever, but maybe we can move on unless anyone's got any burning questions for Irene.